Hey there, Mr. Kern here. This is basically an overview of heat and how it works to make gases do what gases do. So we're going to look at how heat is transferred to things and then what happens because of it. So a couple things to keep in mind. Number one, nature will always try to even things out. So whether it's temperature or the fact that buildings are tall and the ground is low and nature tries to knock them down, nature always tries to even everything out. So, if you have something that's hot and something that's cold, hot things will send their energy to cold things. That's evening it up, so it'll send it over there. Cold things will suck the energy from hot things. So, as this temperature goes down, that temperature is going to go up. Nature evens it out. Looking at pressure. If you have high pressure, that means there's a whole lot of gas in this area, and it's going to try and even it out by pushing over toward a low pressure area. So the push is going to be in this direction. So at the same time, if you have a low pressure area, that's the place that sucks. Sucking doesn't really happen. It's not real. Well, all that happens is that it's the other end of the push. So it's kind of the pull. But the air is going to flow over here and start to fill up this area more. So a low pressure area just means it needs some stuff to fill it up. A high pressure means they've got extra air and it's going to have to go somewhere. So keeping these things in mind helps you think about pressure and temperature and the fact that nature will always try and even things out. So first off, we're going to look at transferring heat. What we mean by heat is energy. Today I'm going to say energy as that because it's a lot easier for me to write that quickly. So energy. If I were you, I'd write energy like that because it's quicker. But if you want to write in energy, the word energy, do that. It's your notes. So if you need to do that to remember stuff, go for it. If you have something around you right now, feel a metal object and then feel a wooden or plastic object. Usually, the metal's going to feel cold, but the wood won't. The wood will feel at least kind of warm. But if they're in the same room, they have the same temperature. They've been in here for a while. Nature evens everything out. So everything in this room right now has the same temperature, but they feel different. So we're going to look at why first off. So understanding how the heat gets transferred helps you understand basically how we live with all this stuff. So these have the same temperature. It's equal to the room temperature. That's what this is saying. So if you feel cold, that means you got energy sucked out of you. It's like we said, hot things give off their heat. But if you feel cold on your hand, that means something is sucking the heat out, and it's going over there. That leaves your hand with less heat. Less heat, it's cold. So the best example I have of this is looking at bleachers. So if you have bleachers, you have two options. You have the bleachers that are made out of wood, or the bleachers that are made out of aluminum or some kind of metal. Most places go with aluminum because it's cheaper and you don't have to maintain it, paint it or anything. So that's what most places have. But what you're looking at is a conductor versus an insulator. So metal is a conductor. Conductor means it lets energy travel through it very quickly. You should write that down maybe. Energy travels through it quickly. An insulator doesn't do that. So transfers energy, doesn't transfer energy. That's the difference between a conductor and an insulator. So let's say you're on some wood bleachers or some aluminum bleachers. You have extremely long legs for whatever reason. Your body's about 98 degrees. Let's say it's pretty cold out. You're watching a late in the season football game. It's 40 degrees out. So because the air is 40 degrees, the wood and the aluminum will go 40 degrees too, because nature evens it all out. But we have a problem here. These aren't even. So nature is going to move things. It's going to move the energy. It's going to try and move the energy from your butt into the bleachers. The difference between those, I guess, if you're sitting on them, which one feels colder? Just like in your room, if you grab a piece of metal right now, metal feels cold, that doesn't feel as cold. The aluminum's a conductor. Energy is going to transfer through it more easily. So you start to load up basically this part where you sit with a whole lot of energy. Now also, because aluminum is a conductor, that energy is going to flow all the way through it. So it gets really spread out. It's not all built up in one spot. So let's say you get up and you go, get some popcorn. Somebody else comes and sits down. If they sit down on wood, now wood didn't suck as much energy out of your rear as the aluminum did, but because it's a insulator, all the energy kind of stayed right there. So if you go to take somebody's spot, you sit down on wood, it could be warm because all the energy is just bunched up right on the seat. If you sit down on aluminum, it's more likely that it just all got spread out. So that's one kind of real life difference between a conductor and an insulator, is just how well it pulls the energy out from something. That's why we don't have wooden pans to cook in. Because if you cooked in a wooden pan, all the heat would just get right there in the bottom. It wouldn't go into your food. Even if you have like a small burner and a big pan, the heat goes out of the burner and goes all through the pan, so it all gets mixed up really well. So, conductor versus insulator, that's going to lead to different properties. Now with these, if you sit on these, your butt feels colder on this. That means you lost more energy. They have the same temperature though. The wood was 40, the aluminum was 40, but your butt lost more energy on this side. That's why it feels colder. On the other hand, like that's from our perspective, you get colder. But if one object ends up feeling colder, the other object ends up feeling warmer. So it'll end up that the temperature goes from 40 up to something else. So if you touch something that's cold, it's touching you thinking, wow, that hand's really warm. If whatever you're touching can think. Alright, so on your notes of this, just get a section of it and split it up into 3 columns. We're going to look at what are the characteristics of gases as they're moving around like this, the particles moving around like this, compared to gases that are all, woo, I'm a gas, and moving all crazily. Okay? And we're also going to look at the transfer. What is happening as I go from this to that? Or what's happening as I go from this to that? So set it up, 3 columns, it goes around this low, so you don't have to put too much in there. Alright, so again, the idea is these are gas particles that aren't moving very much, or just some kind of particles that aren't moving very much. So their particles are just doing this. This is the particle dance, by the way. It's helpful if you do this too, while we talk about it. And on the test, if you're like, it helps you answer stuff. No one does it because they don't want to look silly, but they would be correct most of the time. Alright, so first off, which of these looks cold? That one, particles aren't moving. That's low energy, so yeah, that's going to be the cold side. So how do we go from cold to hot? What do we have to do? From cold to hot, if this object gains energy, it will start to move around more. The particles move faster. How do we go from hot to cold? You lose energy. So it's that simple. This is what the rest of this will look like. We'll look at how do we go from cold to hot. Then on the test, you'll be able to think about all of these things on this side and how they fit together. So hot, you're going to connect with the other things that live on this side. On the test, it'll be, what happens if I reduce the pressure? Well, what happens if I reduce the pressure? Low pressure was on this side, so that's what it means. So connecting these ideas will help you out a lot. All right, so low energy versus high energy, because we just talked about the energy. So low energy, the ones that aren't moving around very much, that would be cold. So you're connecting the idea of low energy and high energy. How do you go from low energy to high energy? What do we do with an object if we want to increase the energy of it? So energy is the same thing as heat. So add some heat or increase the temperature. Kind of 2 slightly different things. So increase the temperature, now they're moving around a whole bunch. Just think about you when you get hyper, you have a lot more energy. You go the opposite way, take this guy, take away its energy, and it turns into that one, where it's barely moving, it's cold, it's got low energy, it has a low temperature. So we can put temp here too. I can find my pen. if you didn't already understand that cold is the same as low temperature. Alright, so next up, if we're going to look at how the particles are moving. So one side moves slow, the other moves fast. Like I said, if you have more energy, you're going to be moving faster. So ways to get particles to move slower or faster, other than adding heat, well, that's basically it, just adding heat. So these same items would work down here too. But let's not do that. Alright, so next up, looking at pressure. If you think of pressure, a good definition is colliding particles. How much are the particles going to hit each other? Right now, they're not moving very much. Here, they're moving a whole lot. So it's more likely these guys are going to hit each other. If you blindfold a bunch of kids, threw them in a room, which don't do that, you get sued. You blindfold a bunch of kids, throw them in a room. If they walk around, they don't hit very much. If they ran around, they'd smack each other and fall down and they get lawsuits. So don't do that. Okay, but overall, how to change the pressure with these, one way would be to add some more molecules. So if you have 3 kids that you throw in a room and they walk around and don't hit each other very much, if you have 20 kids, they're going to collide a lot more. So add molecules, or the other way is to squeeze it. So if you have a little balloon, if you want to add pressure, just squeeze. Now that moves it around all over, so a balloon may not be the best thing to show it. Maybe if we had something that didn't let some of the things escape. So if we had a solid, a more solid container where we push it down, and it isn't able to kind of change its shape. But adding more molecules or squeezing increases the pressure. So the opposite way, take away some molecules. So if you release some of the air from your tires, that would lower the pressure. There are fewer things to hit each other. Or instead of squeezing, if you release it, suddenly, especially if the release, I think, makes sense with particle dance. So, squeezing things down, I'm moving around a whole bunch. Woo! If I get squeezed down, I'm now shrunken here. So, particles moving around, they want to be a gas, but they can't. And so, if you release the pressure, suddenly there's nothing pushing on this anymore, and so it can pop out again. Okay, energy-wise, if things are down here, they have low energy. When they go out here, they have high energy. So it takes energy to do that, which we see right here. So if we release the pressure, that usually goes along with a gain in energy. All right. So the last thing, examples that we'll look at with these are a liquid would be more like this, a gas would be more like this. And so when we talk about refrigeration, refrigerators work basically on just these concepts. Increasing pressure to squeeze a liquid into, or to squeeze a gas into a liquid. Then you release the pressure to go back to this side, release pressure, but that also gains energy. If it gains energy, it takes it away from somewhere else. So the last thing with this whole idea is, in technical terms, called the kinetic theory of gases. That's the whole, this is the kinetic theory of gases, is this, the idea. It's really mind-blowing. Gases move around. Pretty much it. Some move faster, some move slower. They hit each other and then bounce off. This molecule doesn't care about what this molecule is doing. They just do whatever they want. But that's the kinetic theory of gases, is particles. Gases. We have a special guest speaker today.
Are we on right now?
We're on.
We're on?
Live.
Hey, we're learning about gases today. Gases are important for a number of reasons. They expand. Gases do expand.
They do.
They can fuel things. Gases can fuel things.
It's a different gas.
And different kinds of gases. We're talking all the spectrum of gases. And it's an easy word to spell. Unlike adamantium, which is very different.
What always bothers me is gases looks like it should be pronounced gases.
Gases? Oh, yeah. You throw an E in there, yeah.
Well, it's like you need a double S.
Yeah.
Like, technically,
To block that off,
to make
yeah.
it sound like gases. that
Yeah, because
bothers
you got
me.
that vowel right after the consonant.
Yeah.
To make it sound like gay. So we're
Can't
very
do that.
close right now. Our faces are very close
Uh-huh.
together. Are people going to watch this on the TV box?
I think on the
Okay.
computer box
Can they-
too.
Can they tweet her about it later?
I think they.
That's exciting. All right, well, I'll face Spacey. I'll see you later.
Okay. That was Mr. Little. All right. One last thing with this is just some terminology. As we go from a solid to a liquid to a gas, what is it called? Because you need to know these ideas. Pretty simple. Solid to a liquid, it's called melting. Liquid to a solid, it's called freezing. Those are pretty tough. Liquid to a gas, you can just call it boiling in general. If something boils, it goes from liquid to a gas. Technically, it's evaporation. Usually, I think we think of boiling as needing heat to happen, but we saw with our gas labs, you don't need heat to boil things. It just is liquid turning into a gas. The opposite is condensation. If a gas condenses into a liquid. Now, the example, because I'll usually ask in class, what is it called when a gas turns into a liquid? Crickets. Nothing. What is it called when the side of your pop can gets wet? Condensation. Okay, so that's what it is. Gas condenses into a liquid, so just think of your pop can. And then the big brain buster is when a solid turns into a gas. So think of dry ice. Dry ice. Solid turns into a gas. That is called sublimation or subliming. Sublimation, yes, it sublimes. I don't know gas to solid. I've never heard someone actually use that. You should look it up or something. But yeah, so solid to a gas is subliming. The best example is dry ice. All right, other than that, I mean, these are the basic concepts. If you get this and how these things work together, if I say, what if something's moving fast with its particles? What does that tell you about it? You should be able to link all these things together. What if something loses its energy? What happens to it? It gets colder, it has a lower temperature, the particles slow down, it's exerting lower pressure. So that's what we're looking for. Next video is how refrigerators work, which is a whole kind of other idea, but using these same topics that I just wrote all over. So that's it. Bye-bye.